we continue our session. And the second talk of today is Dr. Hao, University of Geneva, and she will speak about the organization of Virasoro conformal blocks at C equal to 1.
Thank you for the introduction, and I really appreciate the opportunity to speak here. I also want to thank the organizers for organizing this nice workshop. In this talk, I will describe a joint work in progress with Andy Nysky on the Abelianization of Virasoro conformal blocks at C equals 1. So the two-dimensional conformal field theory is a very fruitful research area. It is important not only because it sets the foundation to the string theory, but also because it has lots of interesting connections to other fields of physics and math. In the 2D CFT, the essential objects to study are the conformal blocks. So in short, they are solutions to the word identities. And in my talk here, we will only look at the chiral parts. And indeed, the main objects of my talk today will be the chiral conformal blocks. So I will give a quick review of the definitions of conformal blocks later. But for here, I just want to list the data a conformal block depends on. First of all, we need a vertex algebra. An example here is the Virasoro algebra. And we also need to specify a Riemann surface which can be punctured. And at the punctures, we can insert primary fields. So notice that in general, conformal blocks will form an infinite dimensional vector space. And actually, there will be two types of conformal blocks we are interested in this talk, which are the Virasoro conformal blocks and the Heisenberg conformal blocks. So both of the spaces of conformal blocks for those two algebras are of infinite dimensional. But luckily, we do have actions on those infinite dimensional vector space. So those are given by the Walinde operators, which are originally defined in physics. So they are the original Walinde line operators L gamma acting on the space of Virasoro conformal blocks. And there are also the abelian version, the abelian Walinde operators acting on the space of Heisenberg blocks. So what's good about having those actions on this infinite dimensional vector spaces is that we can use the eigenblocks of them, which will give us a one-dimensional subspace of this infinite dimensional space. So up to this point, I have been talking about some general backgrounds, and now I want to focus more on our work. So the main object we study in our work is the Virasoro block. As we know, the Virasoro algebra depends on a central charge, and our work is focusing on this particular case where the central charge is just 1. And the C equals 1 Virasoro blocks are especially interesting for the following reason. So the first one is that the Walinde line operators, they are not always commuting with each other, but at this special phase, they are actually all commuting, so we can diagonalize them simultaneously and arrive at a one-dimensional subspace. And the second one is because the C equals 1 Virasoro blocks, some particular types of them, have been proven to give the tau functions of the Panevet equations. And the C equals 1 Virasoro blocks are also related to some very interesting dualities in physics, which is in this case, the do for the limit of the topological string and spectral theory correspondence. So the C equals 1 Virasoro blocks are very interesting and important, but they are also in general hard to compute. And the main goal of our work is to provide a new way to construct the C equals 1 Virasoro blocks. And to be more specific, what we do is to construct a non-abelianization map to construct the Virasoro blocks at C equals 1 from the Heisenberg blocks, which we treat as some abelian objects. And here, we do need to give some requirements on the Riemann surfaces. So we require that the Riemann surface for the Heisenberg side should be a branched double cover of the Riemann surface we want to use for the Virasoro blocks. And here is how this double cover going to be shown in this talk. So this line on the base represents C, and the two curves on the top represents the two sheets of C tilde. So there is some projection map to go from one to the other. And because this is a branched double cover, we have some orange cross, which corresponds to where the two sheets of C tilde collide. This is just a branch point. So our non-Abelianization map is actually to reduce the harder computation of the Virasoro blocks to the easier ones of the Heisenberg blocks. So, and here I want to say one more word about why we treat it as some simple abelian objects. So, first of all, the Heisenberg algebra has another name, which is the FNU1 vertex algebra. So from this point of view, naively, it's some abelian object. But more important is because that the Heisenberg algebra is the vertex algebra behind the free boson theory. And we know that the free field theory, they are like much simpler and more fundamental. So, and I want to show you actually later in this talk that the Heisenberg blocks, they can be solved exactly by hand. So this kind of free field realization idea actually has already been explored by people before, and I want to emphasize that the important new idea in our work is to use the spectral network. And just as a heads up, the advantage of introducing the spectral network into the story is that this will differ from the special conformal blocks built before by other work. And we will arrive at more interesting conformal blocks as we will see later. So here is an outline of my talk today. I will start with defining the conformal blocks better. And then after we have a better idea, I will construct this non-Abelianization map in our work. And then I will talk about some applications of this non-Abelianization construction. Okay, so in this talk, we will only see two types of conformal blocks, the Heisenberg one and the Virasoro one. And let me start with dealing with the simpler one here, which is the Heisenberg conformal blocks. So the vertex algebra here is the Heisenberg algebra, which is generated by one field J with this OPE relation, where the singular term is a second order pole. So this C is just a local coordinate around P and Q when they get close. And if we want to see the usual FNU1 algebra, we can do a mode expansion of this generator, and G and Jm will satisfy this commutation relation. So after having this data, we can define a conformal block in, so here by conf C tilde Heisenberg, I mean the space of Heisenberg conformal blocks over C tilde. So to define a conformal block here, we define it to be a system of n-point correlation functions where the insertions are just the generator of the Heisenberg algebra, and this n can be arbitrary non-negative integer. And here the pi's give the insertion point on C tilde, and the i's on the subscription just mean the local coordinate around each point pi. And in the definition, we require that all those correlation functions should be holomorphic if they are away from the diagonal, which means pi equals bj. And at the diagonal, the singular behavior should be controlled by the JJOPE, which is in the definition of the Heisenberg algebra. And we also need to require that under change of coordinates, J should transform as a one form. So I have promised in the introduction that the Heisenberg blocks are simpler objects and we can construct them by hand. That's why we want to express the harder ones using them. And here I want to try to give you some examples to show this point. But to show the Heisenberg conformal blocks, first of all, we need to be able to even pick a point in this infinite dimensional vector space. And here we need to use the abelian Wallinde operators. So for simplicity, sometimes I will neglect abelian, but it should be clear from the context. Okay, so actually, as many other quantities in the so on the Heisenberg side, the abelian Wallin-Day operators, they have a explicit expression. So here, the Wallin-Day operators L gamma for a loop in the first homology class of C tilde is just the exponential of some operator little case L gamma. We will give a name for those L gammas as the log Wallin-Day operator, and they can be expressed as the integral of this generator J around a loop gamma. And I mentioned earlier that if you diagonalize all the abelian Wallin-Day operators, you will arrive at a one-dimensional subspace here. And actually, there is another way to get a one-dimensional subspace, which is by diagonalizing the log Wallin-Day operators corresponding to half of the cycles. And actually, it is easier to first do this. So now what I'm going to show you is how to diagonalize half of the log Wallin-Day operators. So we know that we can do some explicit calculation to show that when we have different loops, the L gamma has this commutation relation. And this is also because, and the commutator is given by the intersection number of the two loops, gamma and gamma prime. So because they are not all commuting, this is also the reason why we can just diagonalize half of them. And it's more convenient if we first fix a choice of A and B cycles with the intersection condition such that the intersection number is delta ij. And now I will just diagonalize all the log Wallin-Day operators for the A cycle. And here, a common eigenblock of all those LAs are given by this condition, where AIs are some parameter we fixed, which will serve as the eigenvalues. And after doing so, we will arrive at a one-dimensional subspace of this infinite space of conformal blocks. So in order to further come to a point in this one-dimensional subspace, we need to fix some normalizations, which in this case is just a function of A. And we fix this by requiring LB acting on psi tilde A by this 2 pi I partial AI. And this will fix the degrees of freedom of the coefficients of those AIs. And as we can see, so this condition and this condition indeed satisfy the commutation relation upstairs. And in order to fix the remaining constant for this normalization, we further require that the 0-point function in these conformal blocks with A equals 0 to be 1. So after doing so, we will arrive at a point in this space of Heisenberg conformal blocks over C tilde.
So, sorry, but how does this L act on psi? So psi is like a conformal block, it's a correlation.
So conformal block here we defined to be an infinite set of correlation functions.
Yeah, but it's a correlation function. L contains J. J is an operator.
Yes, you just insert it in the correlation function.
Okay, so you insert. Okay.
Yes.
Okay, so you're not taking a function, but you're inserting it under the correlation.
Yes. Thank you for the question. And okay, so now we have a way to specify a point in this infinite dimensional vector space. And now I'm going to show you some examples about what are those conformal blocks are. And here I'm taking the example where C is non-punctured. And for the psi tilde A we just talked about, the first several n-point functions just have this explicit expression where all the quantities appearing here are from the Riemann surface. So here, this tau ij is just the period matrix, and this eta A is just a holomorphic one form built from this basis of the holomorphic one form and AI. So there will be a BPQ which starts to appear from the 2-point correlation function, and it is just the Bergman kernel of the Riemann surface. I hope this can convince you a little bit that we indeed have a way to calculate the Heisenberg blocks by hand. Yes.
Maybe it would be more clear if you say more strictly what is the definition of these brackets with psi. Is there any definition of that? You say implicitly that, like, answering to your question, that if you insert under such correlation current, then it acts either by A
Yes.
or by DDA. But do you have any explicit representation for these brackets? Is it a matrix element for some states in the representation of Heisenberg algebra or something like that?
Are you asking whether I can explain it as the
For example,
line?
the first formula, the top one, where from it's come. Yeah, we can check that A equals to 0 is unity.
Yes.
Yeah, but so how to derive it from what?
So you just use the condition about, so first of all, you need to require this kind of singularity condition coming from the definition of the conformal blocks, and then you require that LA and LB acts on it by inserting this thing over there.
So you mean that it's just some consistency with this local properties of
Yes.
algebra and this formula?
Yes.
And that's enough?
Yes.
But if you want to fix it, you just cut the surface over all the cycles, so you get some collection of trinomials and say that the charges there are precisely the eigenvalues.
Yes. Okay, and actually, so up to this point, I just talked about the non-punctured Riemann surfaces. We can also talk about more generic cases. And for example, we can have primary fields inserted at the punctures. And here, I just want to show quickly the definition of a conformal block with those extra insertions of primary fields, which is represented by this V alpha Qi. And here again, Qi are the insertion points of those fields, and the alpha i's are some weight parameters corresponding to the primary fields. So if now we want to define a conformal block psi tilde in this space of Heisenberg conformal blocks with extra insertions from V alpha 1 to V alpha k, we define a correlation function to be a system of, we define a conformal block to be a system of correlation functions where we still have arbitrary number n of insertions of the generator J, but for each correlator, there will be also V alpha 1 to V alpha k inserted. And just as before, if we simply look at this part involving J, we still require the same type of singularity behavior, and we require the same transformation under the change of coordinate. But now, because we have those extra insertions, we need to add a condition for the extra first-order pole coming from the JV OPE. And actually, this is the defining property of the primary field V alpha. So here we do have a first order pole and alpha appear as the coefficient. Okay, so this is the story about the Heisenberg conformal blocks. And now we are coming to the harder part, which is Virasoro conformal block. So analogous to the definition of Heisenberg conformal blocks, a Virasoro conformal block is defined as a system of correlation functions with now arbitrary number of insertions for the generator of the Virasoro algebra, which is the stress energy tensor T. And similar to before, we require that those correlation functions should be holomorphic if no pi equals pj. And when pi equals pj, the singular behavior should be governed by the TTOPE, which is in the definition of the Virasoro algebra. And just as we are familiar with, in the CFT, we always have this transformation of T under the change of coordinates, which is using this Schwarzian derivative term. So the Virasoro conformal blocks are much harder to construct. And here I'm going to talk about our non-Abelianization construction of the Virasoro C equals 1 blocks. So to be more specific, what we are doing is to build a non-Abelianization map, this FW, to go from the space of Heisenberg conformal blocks over C tilde to the space of Virasoro C equals 1 blocks over C. And as said before, here we do need to require this C tilde to be a branched double cover of C. And this subscription here, this W, represents a spectral network. So The spectral networks are originally defined in the work by Galto, Moore, and Nysky. And for this talk, we just need to know that a spectral network consists of trajectories, which we will call walls. So here we have 3 walls. And we require that at the branch point, this orange cross, there will be 3 walls ending at it at an angle 2 pi over 3. So each wall here come with a label ij, and they correspond to the 2 sheets of this double cover C tilde, and they should be alternating. So here is changing from 1, 2 to 2, 1, and 2, 1 to 1, 2. And this dashed line here represents a branch cut, so it has 1, 2 on both sides. Okay, so now I want to start constructing this non-Abelianization map. So first, recall that in the definition of conformal blocks, we require the insertions of the generators for the vertex algebras. So in order to make this map, the first thing I need to tell you is the dictionary between generators. And here is what we are doing. So if we want to insert the generator of Virasoro algebra, this T, on the base at a point P, on the cover, we need to insert the generator of the Heisenberg algebra, this J, at both of the pre-images, P1 and P2, and take this particular combination, where the 2 semicolons on the 2 sides just means the normal ordering. So we can check that with this dictionary, we indeed get the correct OPE if they are away from the branch point. But now you might have a problem, which is if we already have this dictionary and we can insert it to both the Virasoro correlation function and the Heisenberg correlation functions, it seems to already give us a map between the 2 sides. So why do we even need to use the spectral network, and what's the role of it? In order to explain this point, I'm going to first forget about the spectral network. So here I'm using an empty set representing this, and tell you what needs to be improved for this naive non-Abelianization map. So here, I'm going to assume that this map is what we want to go from the space of Heisenberg blocks to the space of Virasoro blocks at c equals 1. And this map is given by simply implementing this dictionary. So if we want to have conformal blocks on the Virasoro side with insertion T, on the Heisenberg side, I'm just going to replace T by this combination coming from the dictionary for a Heisenberg conformal block. Okay, so now I'm going to look at a very specific example of our setup, which I will call the baby example. So everything is very simple here. So both of the Riemann surfaces, this C and C tilde, they are just CP1, and the projection map is given by simply Z goes to Z square. And from this map, it is clear that there are 2 branch points which are at Z equals 0 and Z equals infinity. So I'm going to ignore the details of the calculation and just show you that if we indeed use this F empty site, which is the naive non-Abelianization map coming from the dictionary, what we will get is this equation Tpx, where x is the coordinate, equals 1 over 16x squared. So notice that this equation should be understood as holding in the correlation functions, just as what happened in the CFT. So here, if we indeed get a map whose image is in this space of Virasoro conformal blocks over C, what we should expect is this expression here with the actual correlation functions. And we can see that this is just a 1-point function, but on the right-hand side, we have a term which is, by rewriting it a little bit, we have 1 over 16 xp minus 0 square. So up to this point, you might figure that there is a problem because we require that in the for the correlation functions in the conformal block, they should always be holomorphic if there are no insertions at the same point. And here we just have one insertion, this TP. So there should not be any singularity at all. But we do see this singularity at x equals 0. So this means that there must be an insertion at this point 0. So instead of a map into the conf Virasoro, we will have this extra insertion of the primary field. And in the definition of the conformal blocks with primary fields, we will have this kind of correlation function where we always put some extra WH, so we can indeed have some singularity. And this singularity behavior is determined by the OPE between TP and WH. And from this expression, we can actually read what is the weight of this primary field that is appearing at this point 0. And this is just given by the coefficient, which is just 1/16. And actually, the same thing will also happen at the other branch point, which is this infinity point. So if we simply use this dictionary, instead of a map to the vacuum Virasoro conformal blocks space, we actually get a map into this conf Virasoro equals 1 with extra insertions of W1/16 at each branch point. So this has been this extra insertions W1/16 has been known for a while in the branch free field construction. So using this kind of construction, we can arrive at some very special conformal blocks, but we're still interested in more general conformal blocks, which is this vacuum one, because, for example, if you want to make connection to tau functions, this lives in this kind of space of Virasoro equals 1/C without those extra insertions. So what we need to do is to cancel those unwanted singularities. And in our work, the main new idea we have is to use the spectral network to cancel those extra insertions. To be more precise, what we do is to insert some operator, this EW, corresponding to a spectral network W, into this non-Abelianization map, by which I mean inserting it to the Heisenberg correlation functions. And before I tell you what is this EW, let me first make sure that I explain clearly how this non-Abelianization map with spectral network work. So if we want to have the 0-point correlator in the Virasoro conformal block, instead of just inserting one on the Heisenberg side, we need to insert this EW. And if we want to have the 1-point function on the Virasoro side, instead of just using the dictionary to write down that combination of J, we also need to insert EW. And this should be also remembered for all the other n-point correlators. And now I want to tell you what is this operator EW. So it is the exponential of 1/2 pi I times another operator W for this spectral network. And the spectral network is a union of walls. So this WW can actually be expressed as a summation over W applying to each single wall. So if we just look at one of the wall, this Wj has this expression of the integral along this single wall here. So this CQ is the coordinates of the point Q on the base, but the insertions are actually at the cover. So we will have this Q1 and Q2, which are both of the pre-images, and which order this appear depend on the label of the wall. And the operator appearing in this integrand are just this psi plus minus are just V plus minus 1 as the primary fields for the Heisenberg algebra. And we use this particular name for it because in the language of the fermionization of the Heisenberg fields, they're usually called the free fermions. And the Z1, Z2, which are the coordinates on the cover, are just the lifts of the Z on the base. And now, with this extra EW inserted, we can check again in this baby example. So in this case, the spectral network is very simple. It's just given by three straight lines going from 0 to infinity at an angle 2 pi over 3. So here, this operator is simply the exponential of 1 over 2 pi I integrated over those three half lines. And the integrand is just as before. And by inserting this EW, we can check explicitly that TPX now is just something regular. And we can also check that with this extra insertion of EW, this won't cause any other singularities. So this indicates that instead of a map to the conformal blocks with extra insertions at branch points, now this FW we constructed using the spectral network is indeed a map into the space of vacuum conformal blocks of Virasoro algebra at c equals 1. So I hope this explains a little bit about what is our non-Abelianization map. And here I want to, so the existence of this kind of non-Abelianization map is already interesting by itself in the abstract. But now I'm going to show you something that is also useful. And this is, and of course, if we want it to be useful, we should have a way to understand. Yeah.
What sort of calculation shows that there is no singularity, as you said? So you put this operator, so which is just exponent of diagonal cut, yeah?
Yeah.
If you have many sheets, you cover,
yeah,
that just this is.
So now we're.
L, the number of sheets, current algebra, and that's one of the stuff. And how do you show that the singularity disappears?
So we're just doing the explicit calculation of the correlator, where we expand this EW in terms of, so you will have 1 over 2 pi to the n, and the integral to the n, and we calculate each integral. And there is some technical way to write down what is each integral and taking the infinite sum, or there's some very tricky way to first, well, we can talk more about it later, but there's a way.
Given integral, is to infinity, from some given point to infinity.
There's some regularization we need. Yes. Yes. So in order to make it useful, we can we should have a good understanding of how to specify an element of the Heisenberg block, and then you can apply the map to it. And we have discussed briefly before that we can construct a family of Heisenberg block, which is this psi tilde A. And here I want to mention another family first before I apply the non-Abelianization map to it. So the other family is actually this conformal block, this eigenblock diagonalizing the actual abelian Wallin-Day operators. And those conformal blocks can actually also be built from this psi tilde A we have just seen, which diagonalizes the log Wallin-Day operators on the A cycles. So to build the eigenblock of this capital LAB, let's first look at how they act on this psi tilde A, which we already know. So LAI acts on it as a simple way by just taking the exponential, and LBI acts on it by a shift. This is because LB is the exponential of the little case LB, where the little case LB, as we have been discussing, acts on the psi tilde A as a differential operator. So when you take the exponential of it, you will arrive at a difference operator. And now an eigenblock of the capital LAB can be defined by first fixing some parameters of x1 to xj tilde and y1 to yj tilde, and take this infinite sum over the integer lattice. And here, what appears is just psi tilde A with A replaced by x plus 2 by n. And here you have a factor e to the minus n1. So we can now check that LA acting on this, so it will directly act on this and picking up this e to the x plus 2 pi n, which is a common factor e to the xi for all the terms. And if you apply LBI on set tilde xy, it will also go here and shift a by 2 pi I. But then by redefining this n, we can just get an common factor coming from this factor in the front, which is just e to the y. So we can see that this set tilde xy indeed diagonalizes all the LAI and LBI, and e to the xi and e to the yi are the eigenvalues. And using our explicit formulas for the set tilde A before, we can also write down some explicit examples of set tilde xy, and here's the 0-point function, which is just a theta function. Okay, so now we talked about two families of Heisenberg blocks. I want to apply the non-Abelianization map to it. This non-Abelianization map depends on a choice of the spectral network. I'm going to first use a very special type of spectral network known as the Fenton-Nielsen type, which is adapted to the pair of Pan's decomposition of the surface. So here's an example of the Fenton-Nielsen network where we draw it on the four-punctured sphere. So these black lines are the walls of the Fenton-Nielsen spectral network. So if we apply the non-Abelianization map using this Fenton-Nielsen type of spectral network, we expect that when it acts on set tilde A, we will get a computable Virasoro conformal blocks, which by AJT correspondence is identified with the Nikolsov partition functions. And for this particular example here, we expect it to give us the Nikolsov partition function corresponding to this Coulomb diagram. And you can actually already see some similarities of the two things. And here, for simplicity, I will just neglect all the mass parameter and just use this momentum on the internal leg. And we, sorry? Oh, those are the mass parameters for the punctures. Yes. We also have the other type of Heisenberg blocks, which are those set tilde xy, and we can also apply the non-Abelianization map corresponding to this Fenton-Nielsen type spectral network on them. So recall that set tilde xy has this expression in terms of set tilde A as the infinite sum. Now, if we apply the non-Abelianization map on the two sides, we expect to get this summation over integers of this particular combination. And we are just doing the 0-point function here. And as we said before, we expect it to give the Nikolsov partition function. And now, maybe you have already recognized, we want to explain this one FWP set tilde xy as the tau function. And in this case, this formula is just producing us this kind of key formula expression of the tau function. And the example I have shown here is actually for the four-punctured sphere. So we expect that this kind of expression should give us the key formula for the Panevet 6 equation. Up to this point, we have been using the Fenton-Nielsen type of spectral network, but we can also use the more generic Goncharov spectral networks. And this will still produce us some conformal blocks in the Virasoro algebra. And we conjecture that it should be corresponding to the generic conformal blocks corresponding to some triangulations which appear in the work by Goncharov and Shen in this case. And an example of this will be the strong coupling expansion of the tau function, where the two parameters x and y will be interpreted as the Fault-Gonchar coordinates, which are the initial conditions there.
Can you demonstrate it on this previous example when we had just this point? You said that yeah, here you have to use this definition.
If I want to make connection with the Nekrasov partition function, which comes with this pair of pans decomposition parameter, I should have some way to also see those parameters in our setup. So we will use the Fenton-Nielsen type spectral network.
Because of this, so more or less it's the way to distinguish this intermediate check, yeah?
Yes. So.
And if you use any other spectral network, I don't know what it is, but say Kobe-Cherokee, you say, so what will be here instead of this Nekrasov partition function?
So it will be so this Fenton-Nielsen type of spectral network comes with pairs of a pair of pans decomposition. So it has this parameter corresponding to the one parameter family corresponding to this internal leg and the other coordinate. But if you are using the Fault-Gonchar type coordinate, it corresponds to triangulations. And this is another type of parametrization of the moduli space of connection. In that case, we think what we will get are related to this kind of conjectured conformal blocks in the work by Gonchar and Shen, where they talk about conformal blocks corresponding to the triangulations. But I think really the strong coupling expansion of the tau function is an example here, because like in the work by Coleman, Pietro, and Teschner, for example, they talk about that the explanation of the initial conditions there as the Fault-Gonchar coordinates corresponds to this kind of triangulations. So this is all I want to say about our work. And here I just want to mention briefly some interesting future directions to take. The first one is that we hope that our non-Abelianization construction will provide a unified way to understand different constructions of tau functions. We have already seen this keep type formula. And a very important point, which I don't have time to mention in this talk, is that our Abelianization construction actually is providing a new formula for the Virasoro blocks, which as the Fredholm determinant. So in that sense, we hope to make connection to other Fredholm determinant type of solutions to the tau functions, which appears, for example, in the work by Tracy and Wadham, and also in the work by Alba and her collaborators. And there are also some natural generalizations we are considering. For example, it will be interesting to study the Wn algebra corresponding to C equals n minus 1, because the conformal blocks for the Wn algebras are less studied. But the generalization from this Virasoro non-Abelianization to the Wn non-Abelianization should be doable. And it will also be interesting, of course, if we can go to more generic central charges, which are not equal to 1. And that's the end of my talk. Thank you very much for your attention.
In spite of many questions during the talk, please ask other questions, make other comments.
About when you go to C different from 1, then the loops do not commute anymore, no?
Right, but
what do you think you quantize this Fault-Gonchar space? What is the approach? I mean, you have an idea of what you have to do?
So for the Walinde operator is actually, so when you go to the C equals some rational fraction case, it won't be all commuting, but there will be part of it commuting. So you can still arrive at some finite dimensional subspace. this part is okay, I guess. It's not that easy, but I think we can try something. But the hard part is that for this dictionary between T and J, when C is no longer equal to 1, you will have some extra term depends on partial J, like Q partial J. When Q is not 0, there will be this J. And that part is actually what might be harder to deal with, because when you go along some loop on the base on the cover, you will go to a different J to go from J1 to J2. So that part might need more work to think about.
Other questions?
Yes.
Oh, sorry.
Did you think of any relations to topological recursion?
Yes, it looks actually there's something looking similar, but we still, like for example, the Bergman kernel will appear, this type of thing, but we still don't have a good idea how those two things are related.
It looks very, very close, in fact, especially with your double covering.
Yes.
Anyway, I have the same question which I wanted to ask.
Yes.
But I have another question.
Yes.
You have used at the end Fock and Goncharov coordinates, but there are also Nekrasov, Shetashvili, Rosky coordinates.
You mean if I want to do WKB?
Yes.
So we are thinking about that, but this is not the WKB case yet. We don't have this H bar yet. But probably you need to modify something in order to include this H bar into the story.
Okay. Ask question.
When you said that this spectral network does not produce singularities, did you mean some kind of permutational invariant quantities? Because if you look, for example, just at current or at fermion, it probably should have some jumps across this line.
Yes, if you insert a degenerate field, you will definitely see some jumps. This is also why we want to consider this kind of non-Abelianization map in the beginning. Here I'm mostly talking about if you insert T, you don't want any extra like singularity coming from the spectral network. Yes.
May I ask another question? So do you have already some results in the behavior?
Up to this point, we don't have any results. Like, for example, it would be really interesting if we can get the tau functions, but we are not able to do that yet.
Okay. Other questions? If not, let's. Oh, sure.
Just for the definition of this operators. So what is the ordering of this exponential? Is it somehow fast ordered, or it does not matter?
So set plus sign minus are like so you are talking about you want some normal ordering if there are like some singularities, right?
I'm just asking what can be the problems, or there are no problems at all. Like how is it defined? Is it literally the integral of this terminals raised to the exponential, or is it something complicated?
It's really the exponential of the integral.
I think there should be no problem because they are on different sheets.
Yes.
And they do not have any singularities.
Yes.
Right?
Yes.
That's part of this very initial point.
Do you have your argument to put this extension? Just your argument to decide to put this extension is that it works to cancel the singularity.
You mean whether our work is just to cancel the singularity at branch point?
Yes. You justified this insertion by saying that it cancels the singularity as the job.
Yes.
Good, but do you have other arguments constructing ones? Maybe geometrical.
Yes, there's one related to this point Pasha mentioned. It's like if you have the insertion of degenerate field on the base, you want some because it will gives you this kind of flat connections. And there is this story about the non-Abelianization of flat connections there. So this is another motivation why we are thinking about doing the spectral network.
Okay, I think that answered many questions.
Our chairman is in a rush. We have to finish, right?
We have to finish.
But
Anyway.
we are before time, so.
Yeah, we still have time for questions if you have.
We do what you don't.
I have plenty of time. So if you want to ask.
Well, I was asking many questions, but
You asked many questions. You asked many questions.
All answers are written in my different papers.
I think that you asked as many questions as all other participants. Thank you. And let's